Okay, so talked about this four dot experiment. Now we're going to talk about another experiment that's really good. Um, but we're going to backtrack and we're going to talk. I have to remind uh, y'all about the characteristics of imagistic and symbolic or propositional representations. So we talked about these. Let's focus on spatial medium and point for point correspondence. So imagistic representations, they have a spatial medium associated with them, and that the point in your representation, each point in your representation should correspond to a point in the referent is the idea. Whereas symbolic representations don't have a spatial medium, and so of course there'd be no point for point correspondence. Um, and so yeah, so properties of imagistic representations, right? So one of them is called spatial equivalence. So the spatial arrangement of objects in terms of mental images should correspond to the actual arrangement in the real world. Another thing is that there should be transformational equivalence. So operations performed on images should have the same dynamic characteristics as in the real world, right? And I think probably the best way to talk about this is that uh, the way things are arranged in the real world, the objects in the real world, should correspond to the way they're represented mentally. So that's the spatial equivalence part. And when you do something to the image in the real world, it should have the same dynamic characteristics as in the real world, or sorry, operations performed on images in your head should have the same dynamic and temporal characteristics as in the real world. Okay. So maybe that's not very clear what I'm saying, but hopefully these experiments that I'm going to show you, once you read or hear about those, then you can come back and understand maybe these properties a little better. Okay, so this is called mental rotation. We've talked about mental scanning, size and imagery, and here now we're talking about mental rotation. So in this experiment, participants were shown, let's say, a letter, right? And it was either the letter was either in the correct way, right? So the R was like this, or it was reversed, right? And then so that was one thing, and the task was to figure out if two given stimuli were the same or different. Meaning, like, so for example, I believe that these would be the same, right? This is an R that's in the correct way, or it's not, sorry, it's not flipped, it's not reversed like this one is. So you would say that these two R's are the same, even though you have to rotate one of them, but you don't have to flip it, right? Uh, you don't have to take the edge of the R and turn it over here, right? You have to drag it over here. Whereas, yeah. So, anyways, and so you would say these two are the same. These are the same. I believe these are the same, but this would be different from this, right? And so that's the task. You have to indicate whether the two stimuli, the two R's, are the same or different. And importantly, the other thing that changes is whether is the angle. So uh, sometimes the stimuli were angled at 60 or 240, 0 or 300, right? 120, 180. And the idea is that in order to do this task, you have to, in a sense, rotate one of the stimuli until you hit the same orientation as the other stimulus. And if they match, then you say they're the same. And if they're different, you say that they're different, right? Um, and what they found was that the law, the so if the two stimuli were 0 degrees rotated from each other, so one of them was 0 degrees and the other one was 0 degrees, right? So if you're comparing this stimulus to this stimulus, it would be pretty easy. right? To tell that they're the same, or I mean, sorry, that they're different. And so that would be a pretty fast one. But if you were to compare, say, the 0 to the 60 degrees one, that would take slightly longer. And then you have to compare the 0, let's say, to the 120, that would take longer, even longer. And then 0 to 180, that would, of course, take even more time. So the amount of the amount that you have to rotate one of the stimuli in order to try and match the other one, the larger that difference in orientation, in degrees of orientation, the longer it would take, right? Of course, if it was longer than 180, then you could just rotate the R in the opposite direction. So that's why this is sort of symmetrical, or why it goes back down, right? Okay. This is actually done by Roger Shepard, who died, I think, pretty recently. He was one of the best cognitive psychologists slash cognitive scientists that ever existed, in my opinion. Okay. And so I'm going to do another experiment. Unfortunately, my animations are a little off, but it's the same logic. So basically, participants were given two figures, right, of, I don't know, um, like Tetris pieces, kind of. And you had to determine whether the two uh, objects were the same or different. And the idea was that if these two stimuli, if you have to rotate this one, the more you have to rotate one of these stimuli in order to try and match the other one, the longer it took to make that same decision to say that the pair was the same. And this was true regardless of whether the rotation had to be done in two dimensions, so just either like left or right, or whether they had to be rotated in the third dimension, right? Which strongly suggests that participants were mentally rotating one of the images to get to the other image, try and match the other image, which took as much time as would be needed in order to actually rotate the image physically. And so when the required amount of rotation was larger, the mental rotation decision took longer to do, right? So yeah, response time was proportional to the angle of rotation that was needed, which strongly suggests that participants were mentally rotating the figures. Okay, next video, we'll talk about one challenge to the computer metaphor of cognition of the human mind.